Okay, for the last time, can you see me now? My tab?
Yes, miss, we can see it now.
Okay, great. So let's get started with numerical integration. And it is a way that we approximate integrals, and it is one of the first method we are going to learn. One of the first method that we're going to learn is the trapezoidal rule. So first we'll learn how to derive the trapezoidal rule for integration. So derive the trapezoidal rule for integration. Okay. Now, what you're going to see when you're given an integration is something that looks like this here. So you have an integral from a to b, and you have a function fx times dx. So this one here is your lower limit of integration. And this one here is your upper limit of integration. Okay, and the function is said as the integrand. Now, to find out the value of the integral approximately, let's draw the function and I'll show it to you. So here, if we have a function which looks like okay, this form, and here you have your f of x and your x coordinates, axis, sorry, and we have to approximate this function from some value a until some value, let's say b, right? So how do we approximate the function given the limits of a and b? So what we do is we see their value on the function. So we can draw the line here. And here we have our function values, which one is, you can say the coordinate here is a comma f of a, and here it is b comma f of b, right? So how do we approximate this? To approximate this, we will use a straight line from a to b. So we draw a straight line here, and the area under the curve, or the area of the trapezoid here, is what we approximate in the integral, right? So why we do this, why we use a straight line rather than the curve? Because we actually don't know how to use the curve to find out the area under the curve from the function until, let's say, the axis here. So we don't know how to find out this area. So what we do is we take the trapezoid, we put a straight line from point A to point B, and then we find the area of the trapezoid, because that's what we know how to do. Okay. Now, what would be the formula of the area of trapezoid? So the formula for the area of trapezoid is equal to 1/2 times sum of the length of the length of parallel sides times the perpendicular distance between the parallel sides. Okay. Now, if you write them down, so what would be the sum of the length of the parallel sides? Here, like, you know that this is the length, right? So here from A until f of A, the point here, this is the length of A, and this is the length of B, right? So the length is exactly here, which is f of A for A, and the length of B is here, which is f of B. I hope you are understanding whatever I'm doing. If you do not understand, please let me know. So now if I rewrite it as a formula, that will look like, do I have place here? No. Okay. So if I rewrite this, now it will look like half of the sum of the length of the parallel sides, which is f of A plus f of B times the distance between the parallel sides. So your parallel sides are B and A, so the distance between them would be B minus A, right? So you have B minus A, the distance between them. So writing it nicely now, you have an integral from A to B of the function fx dx, and the formula to calculate this integral by trapezoidal rule is half, or let's say the perpendicular distance first, B minus A times f of A plus f of B divided by 2. So I put the half inside the brackets here so that I can just tell you that this here is some approximation of the value of the function. Some approximation of the value of the function. So some approximation of the average value of the function. Okay. Now, here we don't get the exact average when we calculate f of A plus f of B divided by 2, but we get an approximate of the function average, because if you want to get an exact value, you need like infinite number of points to calculate the exact average. Okay, now let's try to use calculus and geometry to derive the formula. So we just told that for deriving the formula of the trapezoidal rule to find out the integral of a function from A to B, what we can do is, or what we do is, we draw a straight line, right? So a straight line is a first order polynomial. So we will replace the function by a first order polynomial dx. So the 1 is standing for first order polynomial here. Basically the straight line, right? So we have to get the integral of the function, and we put a straight line instead of the function, so we can derive the area under the curve. So now you know that the area of a straight line, or sorry, the equation of a straight line is f of a plus it's f of b minus f of a divided by b minus a. So this is something like an equation of the straight line, as you already know, y is equal to mx plus c, right? So m is the slope. This is over here what we calculated just now is the slope. So times x, which is x minus a plus f of a. Okay. So some of you know it as something like y2 minus y1 over x2 minus x1 and like that. So this is just the equation of a straight line. It's nothing to be confused about. Now, once you have this, we can replace this in the polynomial. So we'll have it like, okay, let me rewrite it again here. So calculating the integral of the function fx dx. We have here the integral of the function first order polynomial dx, and now we will replace the first order polynomial with the formula that we just got, which is f of b minus f of a divided by b minus a times x minus a plus f of a, right? Dx. Now, if you integrate this, you will get here f of a plus, sorry, again, I'm making a mistake here. So this is f of b minus f of a divided by b minus a. This is a constant. And then you have x minus a, the whole squared, divided by 2. That's the integration, the antiderivative. Plus you have f of a x here. So this is in the boundary, or you can say the limits are a to b. We have to integrate it between a and b. And now if you substitute the values of a and b inside the equation here, you will get b minus a times f of a plus f of b divided by 2. So that's how we derive the formula for the trapezoidal rule. There are around 5 ways to derive the formula for the trapezoidal rule. I have only shown you one because all you need to know is how it's being derived. You don't have to learn the ways of derivation because that's not something that will be coming in the exams. So yeah. Now let's work on an example for the trapezoidal rule. So let's work on an example now. Let's take an integral from 0.1 to 1.3, and we have the function 5 times x times e to the power minus 2x dx. So this particular integrand here has applications in all kinds of dynamic systems, whether you're talking about circuits, spring mass, or systems. It's very important here. So we'll find it out using the trapezoidal rule, the approximate value of this integral. So first let's write the formula again. So we have here the formula for the trapezoidal rule is f of x dx is equal to b minus a times f of a plus f of b divided by 2. Okay. Now, I would like you to write me in the text message, the chat box answers. So what is the value for A? Please tell me. Great. So A is 0.1. What is the value for B? (1.3), right? Okay. So our function we know is 5x e to the power minus 2x. Correct. Thank you, I think Khulud, Balkis, and Zora for your answers. Okay, even the rest of you, Yakini, Mariam, Lamia, Ashjan, Basil, Maram, Khalud, Noor, I'm really happy you're participating with me. Okay, now let's go ahead and calculate the integral. So we have to find out the integral from 0.1 to 1.3 of the function 5 times x e to the power minus 2x dx is equal to b minus a, so our b is 1.3 minus 0.1 times f of a. So what is the value for f of a? Can you tell me? So for f of a, we have 5 times x, which is our a we know is 0.1, right? So we have 0.1 times e to the power minus 2 times 0.1. So what is the value of f of a? 0.41. I actually haven't calculated it, so I'll just take your numbers, fingers crossed. So we have here 0.4094. I'm taking the one with more decimal places. And then we have plus f of b. So f of b, which is 1.3. So we have 5 times 1.3 times e to the power minus 2 times 1.3. What is the value for this? Okay, so 0.4827. Okay, divided by 2. Great. So what you get the final result as? Can you tell me that? I'll replace this here by approximate because this is not exact. We are calculating approximate values here. So yeah. So what will be the final answer? Zero 0.535. Okay. Great. Okay, thank you. I will, is it okay if I write what I wrote already because my calculations are based on that? So I'll just write here my value. It's very similar to yours, just a little slight difference. So I have here 0.53530, right? So instead of just 26, I have 30 because I did not do it like separately. I put it all at one time in the calculator. That's why. So here, yeah, we got the approximate value. Now I'll give you the exact value of this integral. So the exact value of this integral, which is 0.1 to 1.35x e to the power minus 2x is equal to 0.89387, right? So there's quite a big difference, as you can see, from what we calculated and what the exact value of the integral is. So let's calculate maybe here the true error. So the true error will be the original 89387 minus the derived value. So we have 0.53530. This is equal to 0.35857, right? Now let's calculate the relative true value error. So we have true value divided by true error divided by true value, absolute times 100. Can you give me this answer here? What is the percentage error that we have now? Perfect, Ashjan, perfect answer. Okay, so we have 387 times 100, and this gives us an error percentage of 40.11%. So as you can see, this is like really high error. This is really high error. What's the reason for having this high error? So if I draw our graph again, so here we have our graph f of x and x here. So yeah, now if I draw it here again, and we have some value a here and some value b here, and what we do is we try to approximate it by drawing a straight line, right? So what value here that we got for the answer 0.53530 is the area of this part here. So we got here 0.53530. But what about this one? Or let me make it red so it shows error. So this is our error, and as you can see, a big percentage of the area was not covered. So this is our error that we have, and it's huge part that we could not cover when we tried to find the area under the curve, right? Okay. Now we can do something to make this better. We can do something to reduce this error. So let's say we create more segments. So currently we only have single segment, but what if we make it, let's say, 2 segments? Okay, so we take our function. Okay, you know our function, sorry, the integral, right? So integral is from 0.1 to 1.35 x e to the power minus 2x dx. So that's our integral. And if we have calculated if you're lost anywhere in between the lecture, please let me know that you didn't understand. So I think you can see my page numbers on screen, so you can just tell me to go to back to some page number. Okay, so here you have fx and x, and let's say our function is this one here. And again, we have to integrate it from 0.1 to 1.3, right? So where you say, let's take another segment, so we come halfway in between here, which is 0.7, and this one here, if we draw another line, so now we have divided this into two segments. And if we draw straight lines between these segments now, so from here we have one segment, and then here we have our second segment, right? Now, the area that we cover now is more higher, if you can see. So now we cover a much higher area, and our area for the error is really, or you can say, has got much smaller, right? Okay. Now, so let me just give you the value. So when we had this one segment, the approximate area under the curve or the integral we got was 0.53530. And now when we are having two segments, so the trapezoid 1 is having the area 0.38175, and the trapezoid 2 has the area 0.40377. So if you add these two up, you get approximately 0.78550 as your area. So you can see that we have got much bigger or much larger area coverage. Like if you remember again, our exact value for this integral is equal to 0.89387, right? So this value here is more closer to the exact value than this one here. So this basically shows that if you increase the segments, the value that we get for the area under the curve becomes better, right? So we can keep making segments here like 3, 4, 10, the number of, how many ever number of segments we like between 0.1 and 1.3. But then our aim is not that. Our aim is to derive a particular formula, right? So that somebody can program it, or somebody can simply put the numbers into the formula and get the answers. So let's derive a multiple segment trapezoidal rule. So let's derive a multiple segment trapezoidal rule. Multiple segment trapezoidal rule is also known as trapezoidal sum. So I hope we don't get confused between these two here. So now again, I'll draw the function for you so I can clearly display what I want to say. So here we have f of x and x-axis, and our function looks like this here. So we have to integrate the function from point A to point B. So from point A to point B. And to do this, we are going to break the area here into n equal segments. So the distance between each segment will be, let's say, h, which is how do you say? So we are trying to divide into n equal segments. So we have the width is b minus a, that's the width of the segment, and we'll divide it into n equal segments. So we'll divide it by n, right? So this is the width of the segment. And here, this is the number of segments. So the distance between each segment is going to be h. Okay, so how will we write it down? Let's say if we're dividing into equal segments here, I'll not write the ones in between. Okay, so here okay, before I go forward, please tell me you all understood up till now, or you didn't. I want to know if you all understood everything up till now. If you all understood everything up till now, tell me yes. Or if you didn't understand, then tell me. Okay. Great. Thank you. Okay. So you all are with me till now. Okay. Great. Okay, let's go ahead. So here now, we know that the distance or the segments are equal width. So here, the distance between each segment in between, we have h, right? So this one here will be a plus h. And then again, we have one more h here. So this will be a plus 2h. But the distance between these two segments is also h, right? So we continue doing this in between. We draw more segments up till how many we want or is given in the question. And then the last segment, the one before the last one, this one here, you can write it as a plus the one before the last, so it's n minus 1 times h, right? So after we break it up into the n segments, then we'll find out the area of these trapezoids. So we'll find out the area of these trapezoids as a single trapezoid separately, and then add them all up to come up with a formula for the multiple segment trapezoidal rule. So let me write the integral again. So the integral again, we have a to b, a function dx. And this function here, we have separated to several segments, right? So for each segment, the integral now looks like what? So for the first segment here, for the first segment, the integral looks like a to a plus h, right? So the lower limit is a for us and the upper limit is a plus h for us now, for the first segment only. And then we have the function dx, and plus we have the second integral from a plus h to a plus 2h. So now for the second integral, this one here, our lower limit is a plus h and our upper limit is a plus 2h, right? And then we have the function f of x dx plus, so we continue for all the segments in between until the last segment. So this is our, you can say the last segment. I don't know how do you represent, how do you say? So I'll just say last. Okay. So the last segment will be having the lower limit as a plus n minus 1 times h to b, the upper limit, function dx. So that's how we separated it into several segments, right? Now, until now, we have no approximation. Until now, these are all proper integrals. But then now when we, for each integral, we write it as, where you say this, the approximate for every single segment trapezoidal rule, we approximate it by the formula for every single segment by the trapezoidal rules. So then that will be an approximate value, right? So how do we approximate it? So, or let's say in normal words, what is the formula for this one here? So you know the formula is the perpendicular distance between the parallel sides. So the first two parallel sides is a and a plus h, which is supposed to be a plus h minus a. So you have h at the in after you do that thing. Anyway, normally if you want to just look at it and see, so the width or the perpendicular distance between the two parallel sides is h, right? So we can see it already here, it's h. So instead of writing b minus a, I will just write it h times, you have now the average value of the function, which is f of a, the two parallel sides, right? So the first parallel side is for us is a, the second parallel side for us is a plus h, right? So you have f of a divided plus f of a plus h divided by 2. That's an, okay, this is approximation, so to change it to approximation. So now we are approximating the integral of the first trapezoid by this formula here, just like what we learned before sometime, using the same formula. And then we have here plus again h times f of, can you tell me what would be here? F of what? F of a plus h, yes. So now we are in the second trapezoid, and we have to have f of a plus h plus f of what for the next one? Correct, yeah. So then for the next one, we have f of 2 plus h, right? And here we divide it by 2, plus we have more segments in between, and we do it for the last segment. Now we have h times f of a plus n minus 1 times h, plus we have f of b, and this one here is divided by 2. Okay, now we have approximated each value here, and now if we write it, actually I need to go to the next spread. I don't want to go till now. Okay, so now we can see something in common in all of this. We can see h, everything has h and then division by 2 and h and then division by 2, right? So we can just take that as common out. So h divided by 2, we can take it as common out. And then we will have here f of a plus, we have f of a plus h here, but then for the next one also we have plus f of a plus h, right? So we have, I don't know if you can see it, we have one f of a plus h here and one f of a plus h here. We have one f of a plus 2h here, and for the next one here we'll also have another f of a plus 2h. And here we have one f of a plus n minus 1h, and in the previous one to this we'll also have the same term, right? So we can write this as here, so we know every time we have 2 times the next where is it, the x value, or some f of a plus h, plus we have again 2 times f of a plus 2h, and so on. It will go until the last one. So we have again 2 times f of a plus n minus 1 times h plus f of b. I think I used too much space. Just rewrite it. Plus 2 times f of a plus n minus 1 times h, plus the last one is not repeated twice, so we have f of b. Okay, I hope until now everything is clear. I don't want to go to the next page as of yet, so you can see clearly what I'm trying to do. Okay, so now we have here our h. We know that the h is actually b minus a divided by n, right? From here, you can see up. So we will replace the h by b minus a divided by n. So we will have here b minus a divided by 2 times n, as we already have the 2. And then here we have f of a plus, again you can see in all of these terms here in the formula before this, we always have a 2 everywhere, right, until the very second last term. So we take the 2 common and we sum all of these terms from I is equal to 1 until the n minus 1 term, all of f of a plus I times h. And then we add the f of b. So that's the formula for multiple segment rule. So this is the final formula for the multiple segment rule. And to say you more precisely, this is very similar to what we have done before, right? So we had here, if you remember, for the trapezoidal rule, when we derived it, we had b minus a times average value of the function, right? So again, we have the same thing here. We have b minus a, the width of the interval, and this here is again calculating the average value of the multiple segment. So here if I said like how many terms here or how many segments are there in total here being divided by 2, and that's how you get the average, that you have the number of you have the different terms divided by the number of terms. So here we have one term plus 2 times, here we have n minus 1 terms, so it's n minus 1 term plus again f of b another term here, so total of 2n terms divided by 2n segments here. So this is also again an average of the function. So we have like how we told at the very beginning, we have the area of the trapezoidal formula is average of the function times the perpendicular distance between the parallel sides. So same is here, we have perpendicular distance between the parallel sides b minus a, and then we have here the formula which shows the average of the function of the multiple segments. So I think, yeah, that's all I had to do for that part there. So now we can move on to an example. Cannot see you writing, miss. Which part? Like if I go back here, the last part you mean? Yeah, I think it's a bit unclear. Okay, I'll rewrite it. So, okay. I will just use a different color, and so I can go a little bit above and right, and you can see it. Yeah. So here we have one term, f of a, and here we have plus 2 times n minus 1 term plus f of b is one term. So when you add all this up, you get 2n terms, right? So we are dividing 2n terms by 2n segments. So this is also an average. Okay, I hope now you could see it. Now if we go to the next part where we again we go for an example now. So we'll go for an multiple segment trapezoidal rule. Example. Okay. We'll use our same integral as before. So we have 0.1 to 1.3. Our function being 5x e to the power minus 2x. You're welcome, Suha. Okay. So here you have dx. And now let's use, let's say, 3 segment for the trapezoidal rule. So we'll use 3 segment trapezoidal rule. All right. Now, can you calculate me the value for h? So while I'm writing down our formula for the trapezoidal rule again, calculate the value for h and give it to me. No, Maram, it's wrong. No, it's wrong. Aisha, correct. Ashjan, I'm not sure. So here we have, yes, no, now you're correct. So here the formula is this one here times f of a, correct, Bashir, plus 2 times the, okay, our bracket doesn't look good. Sigma from I is equal to 1 until n minus 1 of the function a plus I times h plus f of b. Okay, Majid, why 4.33? No, it's wrong. Okay, let's calculate it together. So h, right? So we have h is b minus a over n. As we know, our b is here. Oh, sorry. Yeah, this is b. This is a here, right? So 1.3 minus 0.1 divided by n, and n is the number of segments. So here we have, is Majid, that's correct. So we have here 3 segments, that's n, right? So for n, we'll put 3 here, and that gives us 0.4. All right, now let's start working with our formula. So I think I want to remove the h calculation from here so I can, it's okay. Just know that I'm continuing with this part here, right? So we have integral going from 0.1 to 1.3. Our function is 5 times x e to the power minus 2x dx is equal to b minus a. So we have 1.3 minus 0.1 divided by 2 times n, two times 3, and then we have here f of a, which is f of 0.1, plus we have 2 times summation of I is equal to 1 till n minus 1. So we know our n now is 3. 3 minus 1 is 2. And then we have function a is 0.1 plus I times h. And we have calculated our h is 0.4. And yeah, now we can close this bracket plus f of b, which is 1.3. Okay. Now if we go ahead and calculate this, we'll get 1.2 minus 6, sorry, not minus, divided by 6. And then we have f of 0.1 plus 2 times in brackets. So we have 2 times in, my bracket doesn't look really good. Okay, so now we have here, tell me what would be for the f, the coordinate of x here. It would be f of what? Perfect, Basil. Okay, so here we have 0.1 and I is one for us for the first iteration. So 1 times 0.4 is 0.4, 0.4 plus 0.1 is 0.5, plus we have f of I is 2 now. So 2 times 0.4 is 0.8 plus 0.1 is 0.9, right? Now we have f of 1.3. So if I write it all down, we'll have here 5 times x, which is 0.1 times e to the power minus 2, 0.1, plus we have 2 times in bracket 5 times 0.5 times e to the power minus 2 times 0.5 plus 5 times, so I'm putting all these values inside the function, right? 2 times 0.9, and if I make a mistake, do let me know, because it's a lot of things I have to focus at one time. So e to the power minus 2 times 1.3, 3, and then we have, so we're supposed to put a bracket here. So there is a bracket here and then a plus. Okay, so this is going to give me, okay, can you all calculate and tell me what's your value? From where did we get 0.9? Okay, I will write this in red so you understand when I'm clearing your doubt here. And while I'm creating Fatma's doubt or anyone else who has this doubt, the rest of you please calculate the value for this calculation here. So here, Fatima, we have we are getting these two values from here, right? And this one is an iteration, like this is going for I is equal to 1 and I is equal to 2, right? 1 to 2. So for the first time, we will have f of 0.1 plus I is equal to 1 times 0.4. Plus, for the next summation, we have f of 0.1 plus I is now equal to 2 times 0.4. So if you look at it carefully now, you have f of 0.1 here plus 1 times 0.4. So this whole thing is 0.5. Plus, if you look at this one carefully, you have 2 times 0.4, that's 8, 0.8 plus 0.1. So you have 0.9. Is it clear now, Fatima? From where we got 0.9? Okay. Basil, your answer is correct. Balkis, no. Unfortunately, answer is wrong. Great, Fatima. You're welcome. Okay. Now, if we write our answer, what I calculated, Basil is just one decimal place more than you. So we have 0.8435. Okay, so that's my value. And yeah, now let's compare this with the exact value. So the exact value of this integral is 0.89387. So you can see we came a lot more closer. We came a lot more closer to the exact value now after we made 3 segments, right? Let's calculate our true error now again. I'll just calculate it here. So our true error is 0.89387. That's original value minus the derived value. So that's 84385, which is equal to 0.0 0.5002. And now if we calculate the relative true error, we have the true error divided by the true value times 100. So that is 0.05002 divided by 0.89387 absolute times 100 is equal to 5.5959%. So our error also reduced. If you remember, the first error that we had was 40.11%, but now we just have 5.5959%. And the more number of segments we will do, the more our errors will keep reducing. Okay, because the more area we are covering of the area under the curve. So now let me show you that. So for our example that we had is 5 times x times e to the power minus 2x dx. Here are the separate segments that we calculated, and here are the approximated values that we got. And then we have here the true errors and the relative true errors. So let's start from, we started from one segment, and that time we got our approximated value as 53530, and our true error was 0.35857. And our error percentage was 40.1%. So this is in percentage. And when we took two segments, we got the value as 0.78550, and our true error was 0.10837, and our error was 12.1%. And then we just now saw with three segments, we got the value 0.84385, and then the true error was 0.05002, and the percentage error was 5.60%. Now, if you take four segments, you will get 0.86535. So this one we haven't calculated. You can calculate it by yourself at home and see whether you get exactly the values that I'm giving you. And then the error percentage will be 3.19%. So as you can see, as we increase the number of segments here, so as the number of segments we're increasing, our error percentage is decreasing, right? So multiple segment is, or trapezoidal sum is better than having just trapezoidal rule done. Now, let's work on multiple. Okay, first let me know, up till now everything is clear for all of you? Up till here everything is clear? Okay, okay, great. So now we'll work on, okay, now we'll work on multiple segment trapezoidal rule. Okay, thank you everyone. Trapezoidal rule error. So we'll now work on the error. derivation for the multiple segment. So let me draw the function again here. Okay, looks a bit smaller than before. Okay, now if you have a function and you're calculating from a point A to a point B, the area under the curve, as we already know it, all we get is this area, right? So we have a particular error. So this one here is error that we don't cover when we do single segment. So for single segment, the true error formula is minus 1 over 12 b minus a cubed times second derivative of the function at a certain value alpha. So this alpha is unknown, we don't know about it, but then we know the range of it. So the alpha is in the range from A to B, right? From or in our boundary. So alpha is a value in our boundary. So yeah. Now if you're trying to derive, so it's without any derivation, I directly gave you the for the single segment error, but now we'll derive for the multiple segment error. How do we derive that? So for that, I'll draw the function again. Okay, this is not supposed to be red. And yeah, okay. Now we have our boundaries again, A and B. And we have to divide this into n equal segments. So we already know that we divided to n equal segments and the value between each segment is h. Okay, and here we have this a plus h, here we have a plus 2h, and here we have a plus n minus 1 times h, right? And we know that the width of the segment, or the distance between the parallel sides of each segment, is this h value here. So we'll break the between the points A to B to n equal segments and then find the area of individual trapezoids, and each of these trapezoids will have some true error associated with it. So each of these trapezoids does have, I'm not being accurate actually when I'm drawing this. Let me try to be accurate. So here so close. So each of these separate trapezoids have particular true error that is related to them, right? So how do we get these true errors? So we can just get them by taking all of them separately, like each trapezoid separately, the error of each trapezoid separately. So let's first calculate the error of the first trapezoid here. So just h is equal to b minus a over n. So I'm just writing the formula down there so I can use this space. So for the first trapezoid, we have the true error is minus b minus a. So instead of this b minus a, now we have our own boundaries here, which is a plus h minus a. So this is the upper limit and the lower limit of this particular trapezoid 1, and this is cubed divided by 12. So I'm just following the formula of the single trapezoid error times second derivative of the alpha 1 now. So the alpha 1 is a value that is between a and a plus h. Okay. Now, if we rewrite this here, we know that the distance between a plus h minus a is h, right? So this distance here, it's h, we know it. So h here is cubed minus divided by 12. So I've replaced the a plus h minus a by h here, and that times the second derivative of the function at a certain point alpha 1. So I'll write it here again. So alpha is between a and alpha 1 is between a and a plus h. Now we can try to work out the true error formula for the trapezoid 2 here. So for the second trapezoid, we'll have minus distance between here, the distance between the boundary of this trapezoid is h again here, right? So we have h cubed divided by 12, the second derivative of alpha 2. So alpha 2 lies between a plus h and a plus 2h. Now you can see, how do you say? You can see a format here already, a general format. So we can just replace now the 1 and 2 by a general number I. So E of I will be minus h cubed divided by 12, second derivative of alpha I. And alpha I is in the boundary from a plus I minus 1 times h. We have alpha I here less than b. Or no, not b, but a plus ih. Okay, so that's b actually. So yeah, that's the general formula. So you can say the general formula for true error of multiple segment rule is this one here. And so if I add all of these errors that we have got for all the trapezoids, we reach this one here, which is for the multiple segment trapezoidal rule error. Now we can write here the total true error as, I'll go to the next page now. So we have the total true error is equal to, so again, this is the error for one segment. This one here is the general formula for the error of one segment. right? If you have doubts, please ask me. Now we will calculate, or let me, so this is the error for one segment. We have to calculate the summation of all of these errors. That will give us the error for the multiple segment. So the summation of all of these errors will be summation from I is equal to 1 till n, all of the errors in the general formula that we calculate, right? So now we can say that it is from I is equal to 1 till n. So we'll replace the EI by the general formula that we just calculated, that is minus h cubed divided by 12 times f second derivative of alpha I. And here if we take the constant out, we'll have minus h cubed divided by 12 summation of I is equal to 1 till n f second derivative of alpha I. And then we can replace h by b minus a divided by n. That will give us minus b minus a cubed divided by 12 times n cubed summation from I is equal to 1 till n second derivative of the function at alpha I. So if I rewrite this by changing the n cube down here, so we have minus b minus a the whole cube divided by 12n squared. So I take one of the n on the other side, so we have summation from I is equal to I is equal to 1 till n of the second derivative of the function at alpha I divided by n. So we can rewrite it in this format here. So now if you look at it, this here is an approximation of the second derivative of the function. And this is not a constant, but it is a number which is going towards constant. So the larger the n becomes, the more constant this number becomes. So you can say that it is becoming constant, and then this one here is a constant, and this one here is a constant. The only thing that is changing or varying is the n squared. So you can say that the true error is approximately indirectly proportional to n squared, or you can say it's directly proportional to 1 over n squared, right? So this means that when you double the number of segments, the true error gets quartered. Let's explain this in a little more detail in an example. So let's work on an example for the error now. So I will rewrite this formula here, or yeah, let me rewrite it. So we have the true error is equal to minus b minus a cubed divided by 12n squared. Then we have summation from I is equal to 1 to n second derivative of the function at alpha I divided by n. So as we know, this one here is, this part here is approximately the average of the second derivative of the function, and alpha I is between the values of a plus I minus 1 times h and less than a plus IH. So now if we are given example, a real life example where we have the velocity of a rocket, so we have v of t is equal to 2000 log minus, sorry, not minus here, times 140,000 divided by 140,000 minus 2100t times, sorry, minus 9.8t here. So we are asked to find out the distance covered by this rocket from 8 seconds to 30 seconds, the distance between this time here. So you can see the distance x is equal to the integral from 8 to 30 of v of t dx. So how do we find out the distance that is covered between 8 seconds and 30 seconds? Is we just do the integral of the function from 8 to 30. Now, I have already calculated the values for this. So we have here, let me draw a table. Okay. So we have here n, which is the number of segments, and then we have the approximated values of the function, and then we have the error, the true error, and I'll write them later on. So we have, if we have two segments, we get here approximated value as 11266. So the exact value of this integral is equal to 11061. Now the approximated value is this one here when we have two segments, and the true error is minus, if you subtract from the exact value 11061 minus 11266, you will get 205. And then if you have four segments, the approximated value is 1113. And when you have, so I'm increasing the number of segments by double. So when you have 8 here, you have here 11074, and here when you have 16, you have 11065. And the true error, when you subtract, you get here minus 48, minus 13, and minus 4. So what we said is that the true error, we said, is directly proportional, or you can say approximately directly proportional to 1 over n squared, right? So if we increase or we double the n, the number of segments, the true error will get quartered, will get divided by 4. So let's try to do that. So if we divide the true error here by 4, if we divide this by 4, we'll get here minus 51 times 0.25. And if you divide minus 48, you get here minus 12, and then here minus 3.25 and minus 1. So if you compare, you will see that when you have doubled the number of segments, so if you divide this minus 205 by 4, you get minus 51.5, which is a very close value to minus 48. So you can see that when you double the number of segments, the true error is quartered, it's divided by 4 here. Then if you double that one again, if you divide minus 48 by 4, you get minus 12, which is very close to minus 13. So it's kind of quartered. It's not exactly quartered, but it's approximately quartered, because we have here this here the average value of the second derivative of the function, because that one is changing. It is not yet constant. The more the n grows, the more the number of segment becomes larger, the more constant this is. So the more the number of segments will become larger, the more it will become exact quartered. Okay, so that's what you can see over here, that this one holds true. So when the number of segments are doubling in multiple segment error, the true error is getting quartered. So why I have shown you this numerical analysis here is because this is related to another method of numerical integration, which is Romberg method. So that's a better method than trapezoidal method for numerical integration, and we might cover it in the next few lectures. So that's the end of today's lecture. Let me know if you have any doubts up till now. Or is it clear? Clear. Okay. Okay. Great. Okay, I'm happy everything is clear. So fine. Now I want to talk to you about the tutorial a bit here. Miss, you're going to give us the next lecture. Yes, I'm going to give you all the lectures from now on, actually, because I'm actually currently responsible for the course. Mohammed Al Busaidi, he left. So for your any kind of doubts or any kind of concerns, contact me. I'm alone responsible for this course now. Okay. Thank you, Fatma. Okay, so for the tutorials, I wanted to say you this, that please do attend at the end of the tutorial the conversations with me, because it's us connecting, right? We are not being able to connect in a classroom, but that's the time you to get me one-on-one. So connect with me, talk to me about any doubts, any kind of concerns if you have. And the best thing what you should do is you should watch them at least. I'm not saying it's a must you should ask me question. No, it's fine if you do not have questions and my videos are clear. It's completely fine that you do not attend, but I really have the concern that you all are not watching the videos during the tutorial time. Not even during the tutorial time, but even like 1 week later, I know my views, like I can see you all whether you're watching or not, right? So it's good if you go like now, if you watch them, don't watch it at the end right before the exam, because I saw it during the midterm exam. All of you were watching it right before the exam. That becomes too much, isn't it? Like you get too much of information in one day. How do you manage that? It's better that at least you take 1 hour every day for the numerical mathematics and watch a video and get ahead in your course, learn the things, and then you're able to solve your assignments, know your doubts on time. You can ask me your doubts on time and we can have the conversation before the finals. I do not want even a single student to fail. So I want all of you to pass, because numerical mathematics is really easy. No, we repeated before exam. I know, of course, I know that you repeated before exam. But then I just want you all to even see it when every week the tutorials are happening, the lectures are happening. You should see it on the time. Otherwise, you might have a doubt, but you will have it much later when like we are in the next chapters. That's what I'm saying. Okay, and I would love you all to pass the course with good grades. So please. Okay. Any questions? Anything you want to say me? Or if you have any other concerns, you can email me. And if you have no other doubts for today, we can end the lecture here. You're welcome and thank you for the motivation. Okay. All of you are welcome. Please do attend the lectures and the tutorials if possible. That would be really good and we'll go ahead together. Welcome everyone. See you all in the next lecture then, which is I guess on Thursday. So yeah, and every tutorial also. See you all. Bye-bye.